there we go. Last time we started talking about logarithms. And just to, whoops. Just to kind of recap that a little bit, a logarithm gives us a way to find a missing or an unknown power, right? So logarithms answer questions like, how long would something take? What power of a base is this? That kind of thing. So for example, 5 squared is 25. Just a statement, right? That's an exponential expression. If I take the base 5 and raise it to the second power, what I get is 25. Or if I think about multiplying by 5 and do that twice, 5 times 5 is 25. That same information or that same relationship as a logarithm exponentials have a base. Logs also have a base. The way we write the base for a logarithm is with a subscript like this. And then everything else basically switches places, right? So for the exponential, I think of 2 as being like the input, right? The base controls how the thing works, how it moves, how it changes, what the rule is, kind of. The exponent is saying, okay, well, how many times do you want me to do that, right? How many steps? Okay, 2, fine, 5 times 5. For the logarithm, the same thing's true. The base is, dealing with how the thing works, right? What it's doing. But whereas here, I kind of think of this as being like the answer, right? This is the result I get. For the logarithm, I take the log of that, and what I find is what power of the base we were talking about. So the log base 5 of 25 is 2, because 2 is the power of 5 that gives me 25, right? So 5 raised to the second power gives me 25. Let me just highlight stuff that goes together. And I don't know, call that the answer if you want, I guess. But that's the same thing over here. Okay, so what's the log base 4 of 4? 1. Because the question the log asks is, how many 4s is this, right? How many of these are in here? Just the one copy, right? What's the log base 4 of 16 then? Okay, what's the log base 4 of 1 over 16? Same number, right? Yeah, but the reciprocal, to flip it over, it's negative. So what's happening there is that, if you want like an intermediate step to see where this came from, it's the log base 4 of 4 to the minus 2, right? 1 over 4 squared, so 4 to the minus 2, so negative 2, because what the log does is give me the power on 4 that's in here. Okay, what about the log base 4 of the cube root of 4? Do what? 3? What power of 4 is this thing? 1/3, yeah. So right at you with the 3, but because it's a root, we're not talking 3 copies of 4, right? We're talking about breaking 4 into 3 pieces, so it works the other way. This would be 1/3, because that's the same thing as 4 raised to the 1/3 power. Okay. How about the log base 4 of 4 to the x? How many 4s here? X copies of it, right? 4 to the x means 4 times 4 times 4 times 4 times 4, whatever x times is, right? So how many 4s are in here? Well, that many, right? Notice what's happening. Look here, 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 maybe. The base 4 and the power of 4. The base 4 in the log and the base 4 in the exponential. What are those doing? Canceling, basically, right? I mean, one undoes the other one, right? And what we're left with is just whatever was in the exponent. So what's happening when one function does a thing and another function undoes exactly that thing or does exactly the opposite? That's what's happening, right? We're composing, we're doing one after the other. Yeah.
Question, what happens if the x is outside of the power? The same thing?
Different thing. Yeah, different thing. So this is because what's happening is happening because we're taking the log base 4, which measures how many 4s you have, of a power of 4, which is just shorthand for writing a big product of 4s. So what's happening is happening because of that. But these things basically cancel and we just get whatever the exponent was. So I shouldn't have to do anything at all to figure out what the log base 4 of 4 to the minus 2/7 is, right? Like I don't have to think about what this exponent means. We can, like we have the tools to do that, but I should be able to just write down that the answer is -2/7. Right? Those two things just cancel. Okay. The flip side of that, like doing the same thing but in the other order, is admittedly looks a little bit weirder and doesn't come up as often, but 4 to the log base 4 of 3 would be 3. This is the same thing, just the other way around. A power of 4 raised to a thing that counts powers of 4. Those are basically just going to cancel and we get whatever this was, right? So all of this is that 4 to the x and the log base 4 of x as like functions. Let me write y equals are inverses. They're exactly opposite in what they do. One does a thing, the other undoes exactly that thing. So they, again, always be careful saying cancel, but they cancel, right? They undo each other. Okay. Whatever that sound is coming from inside this room, or is it outside somewhere? I don't know. There's music or something happening. Or I've lost my mind. Yeah, okay. Okay, it's not just me then. Good.
I think it might be the voices.
Okay, yes, the voices.
Yeah.
You hear them too?
It might be them listening to something else.
Yeah, okay. All right. Okay, so that's logs. We got into this a little bit yesterday, but we kind of left off in the middle of things. Let me throw in a problem that's not actually there, but is similar to stuff that's on the notes from the last couple of days. Let's say 2 to the x equals 8. I'm trying to solve that, right? Find the value of x that makes that true. What can we do? Okay, I can just start plugging in numbers. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3rd is, 8. Hey, we landed right on it. Cool. Okay, so 2 to the x is 2 to the 3rd, which means those things have to be the same. So X must be 3. Okay, cool. So basically just like, blind luck, we just kind of stumbled into it, right? Because the problem was, sort of just cute enough that, if I'm clever, I can kind of figure my way out of that. Can we do the same thing there? Yes. Are we as likely to try?
No.
No. Here, without realizing it, maybe you see 2 here and you see 8 here and you go, oh, well, I know that 8's a power of 2, right? So that's why we just start guessing, right? Because we already know that 8's going to be a power of 2, that's going to work out. You probably, or maybe you do, maybe you don't, but at some point I can make that number big enough that we wouldn't. 1024, I probably don't recognize that right off the bat as a power of 2, right? Maybe if you're into computer science or something, but it is though. It's 2 to the 10th. It's in the denominator, so it's 2 to the minus 10. So then, X must be negative 10. But I mean, everybody agrees that like this is not a good like general approach to things, right? Because even when it does work, I'm not always going to recognize it, right? And if these numbers weren't exactly powers of 2, then this doesn't work at all, right? If this had been 9 instead or 10, like we're about to talk about, then I can't just do that. I can get kind of in the ballpark, but not any closer than that. So the other way that we could approach this, 2 to the x equals 8, or 2 to the x equals 1 over 1024, or 2 to the x equals 10, rewrite that thing as a logarithm. How would I rewrite this as a log? The base is 2 of 8 is x. The goal was to solve. That means find x that makes it, find a number x that makes this true. We just did. Now the log base 2 of 8, I need to see if I can clean that up, if I can simplify that at all, right? But we've made this into a thing that's kind of automated for us, right? Now I'm using the logarithm, like now it's an arithmetic problem. It's not I just have to know, or I have to correctly guess what power it is. A calculator knows how to do the log base 2 of 8 for us. And hopefully you've had a chance to figure out how to do that on your device. If not, or if we need to talk about stuff, let me know. But this I can just type into a calculator, x is 3. Okay, cool, great. So how do we solve something like 2 to the x equals 10 then? Well, I can't really do this because I'm not gonna, just guess the correct power of 2 to get 10, right? I can see that, 2, 4, 8, 16. So I know it's between 3 and 4. If I felt like just, plugging and guessing a bunch of stuff on a calculator, maybe I could get a decimal point or two if I spent a long time doing it. But this kind of falls apart then. But that means I can still approach it with a logarithm. 2 to the x equals 10. So I'm looking for an unknown power, which means we use a log. How would you rewrite this as a log? Log base 2 of 10 equals x. And then again, I just punch it into a calculator and I get that's 3.32. This is an exact answer. This is an approximation. Now, when the log happens to come out to an exact thing like this one did, like this one, it was exactly 3. I didn't have to round to get 3. Then we'll go ahead and do that. But if it doesn't clean up nicely, then a lot of times we'll just leave it like this, right? If it was the log base 2 of, well, like this, that doesn't clean up nicely, or I don't know, the log base 3 of 17 or something where it's not going to come out nicely, then we'll just leave it like that. A lot of times, you'll see this in homework and tests and other places. If we're solving a thing just to solve it, right, just for the sake of like working on the mechanics, then probably the exact answer is what we're going to be interested in. If we're doing it in the context of figuring out like, hey, how long does it take to get this much in my bank account or whatever, then probably I'm going to go ahead and round because 3.3 years means a lot more to me than the log base 2 of 10 years. Like, I don't really know how to make sense of that. I do know what this is though, right? Does that make sense? Yeah, cool. And I mean, stuff will always tell you, you know, exact or round your answer, but that's kind of when you'll see those things happen. Okay, cool. I wanted to jump back really quick to, this is from the 6.2 stuff the other day. There are a bunch of equations here. We kind of did a couple, we've kind of skipped most of them. These are all things that you can do by, you know, just thinking through both sides as powers of the same base. So you see, like, there's a lot of stuff related, 3 and 9, right? 5, 125 is the power of 5. 3, 27 is the power of 3, right? So you can do them all that way. Our book calls those type 1 equations, which, like, is weird to me, but whatever. You can do them that way. Let's take a look at number 7. So we can approach this the same way, right? I can figure out a way to just sort of clever my way through this, notice stuff about what's going on, and solve it that way. So looking at this, what do you see? This was one of the last few on there, so it's probably, you know, a little more involved, just using, you know, usual like logic stuff, right? I see that there are exponents on both sides of the equation. And in those, the thing I'm solving for, x shows up in both sides also. Okay, so it's in both places. But the other thing we should notice is that the base here is 2, and the base here is a half. And 2 and a half, those are related, right? I can think of 1/2 as a power of 2. How do you write 1/2 as a power of 2? How do you get a reciprocal using an exponent? Yeah. Oh. So I didn't do anything to the right-hand side. The left-hand side, though, I can write that 1/2 as 2 to the minus 1. Okay, well, if it's 2 to the minus 1, then all raised to the x, what I can do with the left-hand side now is think about how you combine exponents, right? Just rules for powers. If you have a power on something raised to another power, what do? Multiply. So the thing on the left, that's 2 to the -1 times x, or negative x. Right, I multiply those, I get that. Right-hand side, I'm still not changing anything, just bringing it down. Okay, well, what did that get us? We made them equal, right? Now they're equal and they're the same kind of thing, right? So we're doing a, you know, like comparison. 2 raised to this power is the same as 2 raised to this other power. What does that mean? What does that tell us? They got to be the same then, right? They're functions, they're 1 to 1. That means if this happens, then these things have to be the same. So I get to, you know, basically just drop the 2's and compare the exponents. And then we can solve that, right? Now life's a lot easier. We're just solving a linear equation. Add 2x to both sides. I get that x is 1. Well, that's great. Like, once I get my head around that idea, that's pretty straightforward, pretty clean. Like, there's not a whole lot of stuff I have to do there, but it did require me to start by noticing something, right? And that's always kind of dicey, because what if I don't notice it, right? What if I don't see it? And it also only works because those bases are related, right? I can't do the same thing if this had been 1/3 to the x and 2 to the 1 minus 2x. You know, if I just make that little, seemingly like little tweak to things, none of this works anymore, because this isn't a power of 2, so I can't do the same thing, right? Okay, so let's look at another way we can approach this then. So that was sort of the, like, things were just so, everything kind of just fell into place just right. And, you know, I did something kind of clever at the beginning. This is going to be more like the, like brute force, like this kind of would always work kind of way to approach it, right? What I can do is the thing that I have to begin with has exponential stuff in it, right? The thing I want to solve for is stuck up in an exponent, right? I want to figure out what x is, but I don't have x on kind of the, like, the main line, right? I've got x stuck up in an exponent. So what I can do then is use a logarithm. So let's just look at the right-hand side. Don't worry about what's going on over here at all. Right-hand side looks worse to me, right? The thing in the power is more complicated. There's more going on there. Let's look just at that. If I want to get rid of that base 2 raised to the 1 minus 2x thing, what I would need to do is the opposite. And the opposite for a base 2 exponential is a log with base 2 also. Okay, so let's hit the right-hand side of this with the log base 2. What's the log base 2 of 2 to the 1 minus 2x? How many 2's are there in this? This many. So what that does is, you know, effectively those things cancel and we just get 1 minus 2x. Oh, hey, that's good. All right, I got rid of the base 2 thing. I brought the exponent down. Now I have everything, you know, the thing I'm solving for kind of sitting on like the main line, right? It's right there, ready for me to, you know, work on it and solve it. But we did something to one side of the equation, so we got to do it to both, right? Just for emphasis. Yes, kind of. Ignore the x for a second. What's the log base 2 of 1/2? -1, right? Because it's a reciprocal, or your calculator will give that to you, right? The log base 2 of 1/2. That's a thing we can find. That's -1. Okay. But there are x of them there, right? There are like x copies of that sitting there. So this is -1 times x copies of that. This part's -1 times that exponent x that was sitting there. So -x is 1 minus 2x. All the exponential stuff's gone. Now we're just solving the linear equation, push stuff around as usual. And we get x equals 1. This generalizes a lot better, right? This didn't rely on me just kind of catching something at the beginning or the bases being the same. Now, if the bases were different, like this one that I said a second ago, like we absolutely could not do the first way we talked through this. If they were different, this is going to be a lot messier than what we just did. Like it's not going to be as much fun. It's going to look a lot scarier, but the same idea works. Like we can do all the same stuff, just things are going to be a little bit more stuff to manage. But the idea works, like the method that we're using works. Okay. Like I said, we're going to talk a lot more about just solving equations next week. So for now, we're just kind of like starting to get a feel for it a little bit, but that's, you know, kind of how you can approach that with a logarithm. All right. Now to get kind of the final piece of, you know, this like puzzle and how these things relate to each other and how they fit together, let's look at logs as functions. All right, so take a second if you need to like flip back in notes or something to remind yourself of what the graphs of exponentials look like. Yeah. Am I bad at counting? Yes, tests. Yeah, I'm working on those. So again, take a quick look back at notes from, Monday, I guess, I don't know, earlier this week for the graph of an exponential. All right, so let me just make a really small version of this right here. An exponential with b bigger than 1 is going to grow over time, right? So it's increasing. The function looks like this with a horizontal asymptote at y equals 0. Defined everywhere, and the range is the upper half. Okay. Oh, there we go. And if the base is smaller than 1 or between 0 and 1, what happens is that you flip it this way and the thing decays over time instead of growing, right? So if it faces the other way, domain, range, asymptote, all that stuff's exactly the same though. The logarithm is the opposite or the inverse in the sense of how it works, right? So what an exponential does is say, okay, the base is 2, that means we're doubling, right? So that kind of sets the like rule, the growth rate, like how the thing changes. The x values then are like, well, okay, how many steps do you want? How many times do you want to do that, right? That's why the thing grows as quickly as it does, because to get from 1 to the next, you double, right? For a logarithm, you're talking about the inverse. Inverse is swap x and y. They swap domain and range. They reflect over the line y equals x. So if we look at something like 2 to the x and see it pass through one and 2 and 4 and 8 up there, right? The nice points that it's going to hit are going to be the powers of 2 because its base is 2. Then the log that goes with it, the log base 2, is going to be the same thing but flipped over on its side, right? It reflects over the line y equals x. Domain becomes the range. Range becomes the domain. Vertical stuff becomes horizontal stuff and vice versa. Y-intercept becomes the x-intercept, and the coordinates flip too, right? When we find an inverse, what we do is take all the coordinates, all the xy pairs, and swap them. So if I'm talking about the log base 2, the places where I'm going to get like nice coordinates, nice integer points that it goes through are going to be at the powers of 2. The log base 2 of 2 is 1. The log base 2 of 4 is 2, and so on. So what it looks like is that then. The only thing that changes with the base is how steep it is, but it works basically the same way and sits in the same place. So let's think about describing this. What is its domain? 0 to infinity, right? That the domain of the log is the range of the exponential. So what's happening here at the y-axis? An asymptote, right? A vertical one. It approaches but never quite actually gets there. Same picture but flipped over on its side, right? It's got a vertical asymptote at x equals 0. And its domain, 0 to infinity. 0 has got to be open because it doesn't get to that asymptote, right? It just approaches it. What about the range? It's the domain of the exponential, so it's negative infinity to infinity. That means this function, it's increasing, right? It's going up as we read left to right. but it does it really slowly. Exponentials grow really fast. That means their inverse, logarithms, grow really slowly. I mean, look how, sort of shallow this thing is, but if you continue moving out to the right, it does continue moving up just slowly, right? So again, it's the flip side of what we saw with the exponential. The exponential grows really fast, but it keeps going, right? It never like stops or goes asymptotic. This does the same thing, just again, laid over on its side. This x-intercept is at 1, 0, because for any base, the log of 1 is going to be 0, because that means b to the 0 equals 1, and that's always true, right? Okay. What changes when we talk about an exponential that's decaying over time? So the base is smaller than 1. Exponential growth looks like this. Exponential decay flips the other way. If I look at a log where the base is smaller than 1, then it's going to be the inverse to this thing, right? The way these two exponentials compare is that they reflect this way across the y-axis, right? Growth, decay. It's just a reflection this way. How are these two logs going to compare then? X and Y stuff all flips, right? So the reflection here, it's going to be the same shape, same picture, same everything, only reflected upside down, this way. So if the base is between 0 and 1, then the log is going to look like this. But it's going to have the same vertical asymptote and the same domain and the same range. And I keep making infinity, and the same x-intercept and the, 1, 0. And the same everything else. But it's going to flip upside down. Do what? Yeah. Yeah. Which one are you talking about?
If B is greater than 1, it should be sloping other way.
No. Yeah. Are my notes in Blackboard wrong or something?
Yeah. They are. Oh. Yes, they are.
Okay. Yeah, no, sorry, I'll fix that. I graphed the exponential there. I don't know why. How or why that happened, but yeah, no, I'll fix that. Okay, so logs have a vertical asymptote because you can't take the log of 0, right? This would mean finding what power of the base is equal to or gives you 0. Well, it doesn't, because the base is something positive. So they're undefined at 0. They're undefined for anything negative, right? So it doesn't exist over here at all. The domain is the right half of the plane. Up to the point of, moving things around, right? Transformations work the same way they always have. So if you shift it to the right or left, that changes, of course. So let's look at, one of these together. The log base 2 of x minus 1. What does that minus 1 do? Shifts. Which way? Is it inside or outside of what the log does? Outside, so it's going to shift down. Okay. That's going to shift down 1. All right, so let's just look at the log base 2 for a second. I'm going to start by just finding a couple of points just for the sake of, having done it. The log base 2 of x, just to make sure, we kind of see like how that thing's going to work. If I'm just going to plot points here, I'm just going to pick x values and plug them in. right? What happens if I try to plug 0 in? I get that, but what's the log of 0? With any base at all, but with the base 2 in particular. Try it. That would mean what power of 2 is 0? It's undefined, right? The log's going to be undefined for any negative value or for 0, because you can't write 0 or a negative number as a power of whatever your base is, right? Which is always positive by definition. Okay, what about the log of 1? That's 0. What's the next x value where I would get, nice coordinates? What's the log base 2 of 2? 1. What would the next place where things are going to work out nicely that I can do it by hand? 4. Because the log base 2 of 4 is 2, because 4 is 2 squared. 4 is 2 times 2. Okay, next place then, 8. Now the function's still connected in between these, right? It's just that the coordinates are not going to be, nice. It's not going to be stuff that I can write down just by knowing how to multiply by 2. Notice that what the log's doing, the function values, the y values here, are just counting out, right? 0, 1, 2, 3. What are the x values doing? Doubling. So 4 would happen when we get to 16. That's why these things grow so slowly. The y values are just counting up by 1, but every time I do that, what it costs me is doubling the x value. I have to go out twice as far to get to the next one, right? So the next nice point would be 32, 5, 64, 6. I forgot how to count for a second, right? That's why it grows as slowly as it does. Okay, then what we do is shift it down 1. So this point that was at 1, 0, now it's 1, -1. 2, 1 now is 2, 0. 4, 2 would be 4, 1 because of the shift. Does that affect the domain? No. So what is it? 0 to infinity. In the range? It was everything. You moved it down, but still everything. X-intercept? 2, 0. Y-intercept? No. Vertical asymptote? X equals 0. These things are all tied in together here, right? Okay, there we go. I must have stepped on the cord or something. Those things are all tied in together. The domain is 0 but open at 0 to infinity because the vertical asymptote is sitting at 0 and it never actually reaches there. That means there can't be a y-intercept. So if you shift over or something, right? If I shift the thing to the left, that changes. So like the next one, which I'll leave for you to do at home, but this is a log with base 1/2, so it's going to look like that instead, like flipped upside down. But this +3 now is on the inside, which means it's going to shift to the left. So what happens to the domain? It was 0 to infinity, but then I moved everything to the left. So -3. Right, that vertical asymptote is going to sit over here at -3 now. And the graph's going to look something like that. But that changes some things, right? That means there is a y-intercept now, and I need to go find that, which you can do the same way you always do. But it's going to change the way some things behave there, the way some things work. Okay, so I'll let you, finish up that one about the graph specifically, but this idea, what's happening here to here and, tying into the vertical asymptote, there we're thinking about where the thing is defined, right? And I can do that by thinking about transformations like we just did, or if there's more going on, sometimes that's hard to pick out, right? It's hard to, decide here. We can do it in this case, but it might be kind of difficult to figure out what the transformations are and exactly what that means. Or if there's more stuff going on, then maybe like I just can't really do that at all. Like this is not a linear transformation of this function. So that's not one that I can just say like, oh, it moved to the left and stretched out or whatever. So what are we really looking for when we find the domain of these things? Domain's important, right? It tells us where the function's defined. It tells us when we can solve. It tells us when solving gives me, nonsense back, like I get, false positive solutions and stuff. So the question really is, when can we evaluate or take a logarithm? What kinds of things can you take the log of? What kinds of things can you not take the log of? What does it mean to say that the domain here is 0 to infinity? It means that I can't let this, I can't let the thing that I'm taking the log of be negative. If it's negative, the thing's undefined. Or if it's 0, that's why this is, parentheses here, that's why it's open. I can't let it be negative and I can't let it be 0, or I'm going to get something undefined back, right? I don't get a real number. So when can we evaluate a log? When the inside, sometimes that's also called the argument, like the stuff inside the function, is positive. It has to be positive or otherwise the log wouldn't be defined. So it can't be negative, it can't be 0. Well, how can I find the domain of something like, say even like this one? It's x minus 2 on the inside, so I could just do that as a shift, right? X minus 2 moves everything to the right, so the domain would be fine, I just can't touch anything. So it shifts to the right 2, the domain would be 2 to infinity then. Or that's the same thing I get if I solve the inequality x minus 2 greater than 0, right? That's finding where the stuff inside is positive. X bigger than 2, which is the same thing as that. And that's nice to have, because then I'm not only relying on being able to look at it and correctly identify all the details for everything that's happening transformationally, or being able to do that in the first place. So look at like 6, where there's more going on. This is the log, no base written, which means it's base 10, right? The common log. That part doesn't matter so much though, because that just affects like how steep it is, how quickly or slowly it's growing. The 6 minus 3x part though, that's some linear transformation stuff. There's a shift, there's a reflection, there's a stretching thing. They're all happening in the same direction, which means they all kind of, mingle with each other and affect how things work. But what I really need to know is where this is positive. Which I can solve by, sort of doing it directly. Since it's linear, we can do that. Or if I want to just do the figure out where it's 0, which would be when x is 2, and then check to either side of 2. If I try to plug 0 into that, I get the log of 6. Is the log of 6 going to be defined? Like, is that a real number? I don't need to know what it is, but can you take the log of 6? Yeah, punch it into a calculator. If you get an answer back, then the answer is yes. If I plug 4 in, I get the log of -6. Can I take the log of -6? No. That's not going to be a real number. Again, punch it into a calculator, you get some kind of error message, something like that. That doesn't work. That means that the domain here is everything to the left of 2, because one of the things going on in here is a reflection this way. So it flips the whole thing around, right? But again, I don't have to be able to pick that out one by one. I just need to know what makes it work and what makes it not work. Right? Yeah.
If you kept the signs, and you solved the problem, you ended up getting -3x is greater than -6.
And then you divide by -3, right?
Yeah, and then you put the sign.
Right.
So if I were to do the graph that way, would it still be correct?
That works. Yeah, that's the same thing, because that's still less than 2. That's still this. Yeah, just be careful and don't forget about the flipping the sign part, because people tend to drop that. Yeah. Okay, that's it. Y'all have a good day. I'll see you on the next time class happens.